Hello and welcome to this lecture on radioactivity part 2. In this lecture, we will understand nuclear fission and nuclear fusion. It is important to note that both fission and fusion are completely different than radioactivity. What is common is all of them are nuclear phenomena. We'll understand that in detail. As we start, quick summary of the symbols that you'll see. This symbol indicates we are talking about core principle that can be basis for a lot of questions, important to understand. When I'm giving you some easy to remember memory tips, you will see this symbol. And this is when I'm asking you a question you should have already learned by this time. Let's get started. What is nuclear fission? By the name, it is very easy to interpret that. In this process, a heavy nucleus splits into two lighter nucleus. And all of this process is started when it is bombarded with slow moving neutron. So that is also important. Let's have a look at it pictorially. A radioactive isotope of uranium is bombarded with slow moving neutron. As a result of this nucleus becomes unstable and finally it splits into two nucleus. Additionally, three neutrons are produced. So interesting to note, this whole thing started with one neutron and then you have three more neutrons now. Each of this neutron can further collide with another uranium and create fission, again creating three more neutrons, each one of them. So this is how it can result in chain reaction. We'll talk about that in a minute. These two nucleus that have been created, one is of krypton and another is barium. So if you have to look at if you have to sum up the mass on the left and mass on the right side, you should be able to do that. And in fact, there will be some loss of mass, which you will see energy being produced. Mass and energy are interchangeable. So let's understand this in an equation. We started with uranium, bombarded it with slow moving neutron. It produced two nucleus, krypton and barium. It also produced three neutrons. Each of them can participate in next fission reaction. Let's see this chain reaction. Starting with one neutron, bombarding, producing two nucleus, also producing three more neutrons. Each neutron again participating in another fission and then again producing three more neutrons. This process continues. And if you have to note the number of neutrons in each of this stage, we start with one. After the first fission, we have three neutrons. After next series of fissions, we have nine neutrons, and when each of them participate in fission, we have 27. This is how the process continues. So the question is, will it go uncontrolled? Is there a way we can control this? Answer is yes, we can definitely control this. And to control this, cadmium rods are used. One of the property of cadmium rods is it absorbs neutron. So if you introduce the cadmium rods and you introduce them as much as you want to control, so it will start absorbing the neutrons with which you can keep it at a consistent pace, or you can control the pace at which the fission is occurring. What are the applications of fission process that we have just understood? All the nuclear power plants which produce immense amount of energy, they make use of nuclear fission to produce energy. One of the destructive use, unfortunately, is nuclear bombs that have been created. They are also based on nuclear fission process. Now let's understand fusion. Fusion is completely opposite of fission. In this case, two lighter nucleus will be combined to form one heavy nucleus. But what is the trigger? Trigger is very high temperature and high pressure. This one also releases a lot of energy. Looking at it pictorially, it happens in multiple stages. Here we are talking about stage 1. So we are starting with two hydrogen, two protons. When they fuse, they create deuterium, and deuterium will only consist of one proton. So where is the other charge? So it also releases positron, and obviously positron is not having same mass as proton. So there is a lot of loss of mass, and that's where loss of mass you will see in the form of energy, and this is the neutrino that is created as part of this reaction. So this is the stage 1. Summary of stage 1 is two hydrogen producing deuterium. Now these, in the next stage, one of these can occur. Two deuterium can combine to form a helium, neutron, and some energy. Two deuterium can also combine to form a tritium, hydrogen, and energy. Now we have tritium also. So deuterium and tritium can combine to form helium, neutron, and energy. So it's very simple to summarize this. Stage 1 is always going to be creation of deuterium. After deuterium formation, deuterium can combine to form helium, deuterium can combine to form hydrogen, and after that, deuterium and tritium can combine to form a helium. In each of this step, a lot of energy is released. In fact, here also a lot of energy is released. So what is the importance of fusion? Fusion is the process behind the energy for sun and stars. They are all based on nuclear fusion phenomenon. In the overall fusion, four hydrogen fuse to produce one helium, and one positron is also produced, and then we get a lot of energy out of it. What are the applications? Hydrogen bomb is a very destructive application of nuclear fusion. Unfortunately, we have not been able to uh, create a way to control the fusion, so energy is still not being created using fusion. So let's quickly compare what is the difference between fission and fusion. First two are very simple, as we understood by the definition. Fission starts by bombarding slow neutron. Fusion starts by creating an environment of very high temperature and high pressure. In fission, heavy nucleus divides, splits. In fusion, lighter nucleus combines. In both the cases, energy is produced. And fission can also result in a chain reaction. It does result in a chain reaction, but it can be controlled with cadmium rods. Fusion, creation of the environment and the whole process controlling is still not achieved. It is still under experimentation. In fission as well as fusion, high energy is produced. In one fission, 190 MeV of energy is produced, whereas in one fusion, 24.7 energy is produced. So this number is much smaller than 190. But for the same mass, fusion will produce higher energy. Why so? Because remember, in case of fission, we are using uranium, which has a nucleus of 235 AMU. In this case, we are using hydrogen, deuterium, tritium. Altogether, it has a AMU of about 5. So 5 versus 235. Hence, if you take the same mass of fuel on both the side, fusion will produce much more energy. Another interesting comparison is fissionable material has to be radioactive, like uranium we talked about. It is very harmful, it requires a lot of caution. Whereas fusionable material that we talked about, hydrogen, it is not at all harmful, it's not radioactive. And then fissionable material like uranium is very limited, whereas hydrogen, which is used in fusion, is abundant. We have a lot of them cheaply available. And the applications, we have seen bombs on both the cases, and energy production so far is only possible with fission. Fusion is under experimentation, but interesting point to note is all the stars and the sun source of energy is the nuclear fusion process. So to memorize, I have just come up with a tip. I am sure you have understood the rationale behind each one of this, but still, if you want some easy way to memorize it, just remember this saying, तोड़ने वाले से जोड़ने वाला बड़ा होता है, right? It's true when it comes to the moral values, and same applies over here. So जोड़ने वाला is fusion and तोड़ने वाला is fission. So fusion will generate more energy based on this, and तोड़ने वाला material is very dangerous. It is radioactive, and as per the saying also, the one who is breaking the relationship has to be dangerous, right? So that's how you can have this analogy. Then Todnewala is doing crime, definitely, right? Because he's breaking the relationship, he's breaking a few things. So that's why it can be controlled by the law. Jodnewala on the other side is not committing any crime, so you cannot control by law, right? So the another comparison of what can be controlled and what cannot be controlled, all of that can be related to this saying. Let's compare all the three processes that we have learned so far in this chapter: radioactivity, nuclear fission, and fusion. First of all, what is the trigger for all of them? This is completely natural, spontaneous. You're not starting it, and it is spontaneous. You exactly don't know what emissions will come out. Whereas fission is started by slow moving neutron. So we are triggering the fission. Same with the fusion, we are creating the environment for very high temperature and pressure. So the summary is only radioactivity is natural. These are being triggered by creating the conditions. Next, what is the outcome? The outcome of radioactive decay is three kind of emissions, whereas in fission and in fusion, the outcome is energy. In fission, heavy is dividing into two nucleus, whereas in fusion, two light nucleus is combining into one heavy nucleus. Radioactivity cannot be controlled at all, and we don't know how much radioactivity will happen when, whereas nuclear fission can be controlled. In case of nuclear fusion, this is still under experimentation. As of now, as of today, we can say that nuclear fusion cannot be controlled. What is common in all three of them? We talked about the differences, but what is common in all three of them? Let me give you the answer. All three are nuclear phenomenon. They are all happening inside the nucleus. We are not talking about electrons, like chemical reaction where electrons participate. We are talking about nucleus in all the three cases. And all of them produce a lot of energy. And obviously energy is produced by loss of mass, so there will be some loss of mass in this process. So that brings another important topic. What is the loss of mass and what is its relationship with the energy that is produced? So we apply Einstein's theory. Einstein established that energy and mass are interchangeable. Whenever there is loss of mass, it will be converted into energy, and the relationship is established by E is equal to mc square, where m represents the loss of mass. Whether it is nuclear fission or nuclear fusion, if you figure out what exactly is the loss of mass, you can apply this formula to derive the energy produced. C here is the constant, which is the speed of light, 3 into 10 raised to power 8. And just fact to note, 1 AMU produces 931 MeV of energy. MeV is the unit, million electron volt. You can express the energy in joules also, but in most of the fission, fusion, and radioactivity, this is the unit that is used. Let's do a quick comparison of energy release in different processes: chemical, fission, and fusion. Although this is not in your course, but it is good to compare all the three. How they're starting, what are the ingredients? In this case, we will have different chemicals. In the case of fission, it is started with uranium and a slow moving neutron. In case of fusion, it is started with deuterium and tritium, producing helium and neutron. What are the fuel used in each one of them? Coal, uranium, deuterium, and tritium. Temperature, very interesting comparison. For chemical reactions, you only need in the range of 700 Kelvin, whereas for fission, you need higher temperature like 1000 Kelvin. But in case of fusion, it is much higher, 10 raised to the power 7 Kelvin. So that is the big difference. Starting condition for fusion is very, very difficult. Energy produced at the same mass, we are saying joules per kilogram. So energy produced is less in chemical, more in fission, and much more in fusion. So that is the important point to note, not necessarily the exact numbers here. So, question. In a radioactive decay, we are not talking about fission or fusion. How do you determine the energy produced? So the answer is very simple. Einstein's principle applies universally. Energy and mass are interchangeable. So even in radioactive decay, you will have to figure out what is the exact loss in mass, and based on that, you can calculate the energy produced. So all the numericals will be based on this principle. You should be able to attempt most of the numericals now. So let's summarize what we have learned so far. We talked about nuclear fission, where one heavy nucleus splits into two. The trigger is slow moving neutron. We also talked about chain reaction because each fission produces three more neutrons. Each of this neutron can further produce cause fission. So this keeps on going. Can we control it? Yes, we can control it with cadmium rods. Now, what are the applications of fission? We talked about the constructive use of it, which is nuclear power plants producing a lot of energy, and a destructive application, which is nuclear bomb. How do we compare fission to radioactivity? Radioactivity is a very natural, spontaneous, unpredictable process, whereas fission is triggered by creating the condition, right? So that is one of the big difference. In both the cases, energy is produced. Let's talk about fusion. Fusion is a case where two lighter nucleus combine to form one heavy nucleus. But most important point is it requires very difficult conditions like high temperature in the range of 10 raised to the power 7 Kelvin and very high pressure. It does produce a lot of energy. More energy than any of the two other processes that we talked about when we are talking at the same mass. What is the overall fusion? Fusion happens in multiple steps. Overall fusion, 4 hydrogen will fuse to produce 1 helium positron and energy. But this happens in multiple steps. One in step number 1, 2 hydrogen will combine to form deuterium. Then deuterium and hydrogen can produce tritium. Then deuterium can produce, or tritium can produce helium and energy. That's the summary that you can again go back and revise. Controlling fusion, it has been very difficult so far. We have not got a lot of success in this process. A lot of experiments are going on. The day we are able to control the fusion, that will be great because we'll be able to produce a lot of energy. Fuel is also abundant for fusion and it is not as harmful as fission's raw material is. Applications. Fusion is the process behind the huge energy that is produced by sun and stars, and the destructive use that we have put to nuclear fusion, unfortunately, is the hydrogen bomb. Quick comparison about energy, very important point, so that's where I've included it multiple times. And finally, not to forget the theory behind energy production. Energy and mass are interchangeable, and this is the relationship between energy produced and the loss of mass. Thank you. If you want to listen to lectures on other topics on physics, chemistry, or biology, do not forget to subscribe to my channel.